Welcome to this is not the seventh, welcome to the eighth video in Introduction to Quantum Field Theory. In this video, we will cover local coordinate systems. So far, we have dealt with fields that have constant coordinate systems. For example, we can define a field such that for, say, some vector a sub mu, the field is equal to 1.5. And then for some other scalar value, it's equal to 2, and then or it's not scalar value, for some other vector, maybe c mu, then this is equal to 3.5. So we can say that this is a constant coordinate system. So at each point A, B, and C where the field is evaluated, then there is a constant coordinate system. But we could shift the coordinates. So can shift the coordinates, which would look like phi mapping to some phi prime, which is, say, just phi plus 1. So this would look like the following. It would be phi prime of a mu is equal to 2.5. Phi prime of b mu is equal to 3. And then we have that phi prime of c mu is equal to 4.5. Physically, these fields should be the same, even though we see that the fields give different values. In reality, it's just a shift of the original field, so physically it should be the same. So how this would be represented is, say I have this right here, and then, or actually what I'll do is I'll just draw this one and then I'll copy it over. So say you have the field which looks like a wave, and it's like this. This is your x direction, and then this is your field value. Well, then it'd be like shifting it. So going from here to here, shifting it is like having an extra value right here. So the x direction is here, but it's now below. So you would have that this is the origin. So this would be the origin, but now your new origin is here. So you have this extra plus 1. So you can see that physically these are the same field, but now your origin is shifted down, or shifted down 1, which increases the value of the field. So shifting the coordinate system down 1 is the same as adding 1 to the field. Shifts of this kind, so right here, this is an example of a global shift. So emphasis on global. And this is called a global shift because it is applied everywhere in space. So at every point in space, the origin is moved down to here by the same amount. So it's global since they are applied equally everywhere. But you can also have local shifts. So I take this, then you can get something called a local shift, where instead of having a constant or a constant thing on here, we can just call this the x-axis. But then the actual uh okay, the actual value could if it wouldn't do that, it could change or go up or do something different. And I'll draw a better one. Let's just say that it looks like this. So you can see that at phi prime, if this line right here, if this line is the origin for each point in space, then the difference is going to be different. For example, you have this distance right here versus this distance right here. You can see clearly that even though they should be the same value, they look different because they have different origin systems. So this is called a local. So this is an example of a local shift. So I'm going to just copy and paste this below. Local shift. So there, at each point x, there are local coordinates that are different from each other. Global, local. But to use local coordinates, we need some kind of mathematical bookkeeper. So we need a bookkeeper to keep track um, of how coordinate systems like in different locations are related. So what we end up doing is I'm just going to copy and paste this here. Is I don't need to copy the whole thing. We take this, you can see that the origin clearly is moving. We're just going to put that there. Well, we call this a right here, or we call this function a, and then it's a function of x. And so we say that the origin here is actually a function itself. It's a. And that function a is going to keep track of how all of these different points are related to each other. So to make this situation easier to analyze, to make this situation easier to analyze, we will assume that spacetime is 1 plus 1 dimensional and discrete. The basis of the space, the basis is E1 and E2, which are perpendicular directions. So I would rather say it this way. E1, E2. So this is the basis for each point n, which has some component in each direction. But remember that because we're considering a discrete spacetime, n1 and n2 take integer values. But because for each point n, there are two bookkeepers. You're going to have A1 n and going to have A2 n. So what are these different A's? So this one it encodes how much the origin at n is shifted relative to the origin at n plus e1. And this is the same, but for e2, or but for n plus e2. So, how exactly should we picture this? Well, let's assume that we have two-dimensional space. I'm just going to draw this direction and this direction. This will be your E1 direction. This will be your E2 direction. Then say we have some point here, and then we have the point n plus E1, and then we have the point n plus E2. So this will be n plus E1, and this will be n plus E2. Well, then the origin, let's just for sake of argument say that the origin is up here. Can have the origin here, just directly above each one of these. We'll have them at different locations. So now there's a link between, or there's a height between each one of these. And then let's say that we have the field values at each point. So let's say that we have field value here, then we have a field value that's a little lower here, and that's actually a little higher here. So these will be the field value at n plus e1. This will be the field value at n. I'm going to write it closer. Field value at n. This will be the field value at n plus e2 right here. Well, then these blue are the origin, and the distance between each of these points given here. So we have that the actual field values are from here or to here in an abstract sense, but they are recorded as being from here to here. So if we take a look and just draw a line that is supposed to be a straight line, it shows the relative difference. Let's see, does it go between these 2 points? Yeah, more or less. So this shows where the difference in the origin is. And so this value right here, that is, or let's write it more clearly like this. This is A1N. And this value right here, so if this goes straight, then let's see how exactly would that look. Oh, cool. So yeah, it looks, you can see there, and you get that this distance here is A2N. So if I wanted to consider the difference between two field values, so say I want to compare the difference between phi n and phi n plus 1, so comparing phi n and phi n plus e1, then let me just denote this comparison. So the change in the field between those 2 points is equal to, first, so the change in the field, right? Let me just write what this would be if this goes to here. So if this goes like this to here, then this difference right here is the change in the field. So we want to consider this change in the field. So first off, we can subtract um, we can subtract phi n from phi n plus e1. So it looks like this. So we have phi plus e1 minus phi of n, and then now there is like, yes, taking this away from here will actually give this value, but shifted by this. So we need to now take away the difference between their origins, the difference between their coordinate systems. So now we take away the difference between their coordinate systems. And this right here is how you actually look at the difference. So you have difference between the fields. They might have different coordinate systems. If they do, then you take away that difference. And this works analogously for this works for this direction as well. You want to find the change in the field here. Well, then it's just going to be phi n plus e2 minus phi n minus a2. So yeah, that's how you do it. gonna say something, but then I'm like, yeah, it's not actually adding anything new. So the way to say that it generalizes is to just say that for a particular direction, the change in the field from n into n plus some direction j is that the field value at that direction in that direction minus the field value that hasn't moved and then minus a j, the difference between them. There. A neat way to think about this is that the quantity, so a neat way to think about this is where the quantity phi n, uh, what do you call it? Cn plus a j n lives in the coordinate system. The coordinate system of the point n plus e j. So a j n transports the n coordinate, the n coordinate system into the n plus e sub j coordinate system. For this reason, a sub j of n is called a connection because it connects the coordinate systems of two different points. So we can switch to a continuous model of space by taking the limit of the discrete space. So in this limit, so now we're going from discrete to continuous. And in the limit, we have first that this is the first quantity that we're considering. And this changes. So now we take the continuous limit. So becomes d sub j at n. This is just the change in notation. What this really means is this up here is equal to the limit as some value epsilon goes to 0. And the value of epsilon here just goes here. We have phi n plus epsilon in the jth direction minus phi n. So all this is doing is it's shifting. It's now looking at distances infinitely small, uh, um, so infinitesimally far away from phi n. So it's looking at these differences here. So if this gets infinitely close to n, then that's what this limit is doing. And then you, of course, have how the difference that's encoded by this function, which this just becomes, this is just the definition of a derivative. So it just becomes the derivative in the jth direction acting on the field, then minus a sub j n. So this implies this, and this then implies, so if we move back to 1 plus 3 dimensions of spacetime, that d mu is equal to, or for a position x mu, is the derivative mu of phi, then minus a mu x mu. So this is technically, there is a step that is made here that is a little technically incorrect, and that is the keeping of phi here. Because we're just looking at the abstract taking the difference here. We can, as we make this jump here, we actually take phi out. So this leads to something called the covariant. You can sometimes call it the covariant gauge derivative, but generally just say covariant. Covariant derivative, where d mu, which depends on some position, is equal to just the partial minus the a mu x mu. So this right here, we will see in future videos that this is the gauge field. And this right here is just the difference between field strengths. So when you take the covariant derivative of a field, you first look at the difference between the field strengths, and then you take away the connection, which turns out the connection is the gauge field. For electromagnetism, the gauge field is the electromagnetic vector potential, and so that would be this here. We'll talk about that more in later videos. Hopefully this just helped with understanding how local coordinates work.